So, welcome. Today we are going to start with the first chapter with ICSE class 10 physics. That is nothing but force. Okay, then the first topic we are starting. I think you remember this thing F equal to ma and all the equations of motion. Let me rewrite this again. Equations of motion. This is from class 9. It will be needed. It is needed. Okay, so these two we had studied for what we call the translational motion. Now, what is translational motion? Let me tell you. If I say this is motion, motion can be divided broadly into two categories. One is translational, another is the rotational. Okay, so what is translational motion and what is rotational motion? Okay, when a body, let's say this body, moves in a particular direction, maybe this direction, maybe this direction, maybe this direction, I don't know, any direction, particular direction, but itself does not move from its position. Like if we, how to explain this, let's say if we push a block, okay, that's what we call the translational motion. Okay, this is translational motion. But now if we say rolling motion, let's say rolling motion, not rolling motion, rotational motion, it's also called rolling motion, but rotational motion is actually you need one thing that is called the axis. So let's say this is a disc, for example. Let me redraw this is a disc. Now this is a paper disc. You just put a pencil through it, and at this point it intersects the paper disc, so this whole pencil becomes the axis. And now if we apply a force in this direction, this wheel will go in this direction, it will just rotate. This is what we call the rotational motion. Now sometimes some bodies exhibit rotation, both rotational and translational motion. I give you an example. Let's say you're bowling. So then when you throw the ball, just if you see it in slow motion, you'll see the ball is revolving on its own while traveling. If you see it in slow motion, you would see that. So this is the main difference between translational motion and rotational motion, and there sometimes a body can exhibit both of them. So this is till this much. Now we will learn something, a very important part in actually this chapter force is actually nothing but rotational motion mechanics. Okay, so we will learn something called the moment of force or torque. I'm going to tell it torque only. And moment of force, never ever in your life never say torque is moment, because there is another concept. Moments are of two types. One is the moment of inertia and there is the moment of force. Okay, so if you say just moment, the torque is a moment, it will not get marks, not a single marks, because moment can be of inertia, can be of force. So better to just write torque, never write moment of inertia. Maybe many people make a mistake there. So what is torque? Basically, what is torque? Let's say I have any irregular shaped any body and its pivot. Oh, I forgot to tell you this, that whenever, let's say I told you this axis, the point where it meets is actually called the pivot. Okay, this is called a pivot. So let's say the pivot is at this point. Let's say call it O. Now as you can see here, if I apply a force, let's say in this direction, F, can you tell me what is torque actually? So what torque is actually, that it is represented as tau. It's a vector quantity. It's nothing but what we will learn later in class 11 called F cross R. What this actually means in simple language is that when you extend F, let's say this is F, the perpendicular distance from O to F is the R, and the product, just know it now, tau is nothing but the product of this F into R. Just remember this now, don't need to write this because this is a little bit advanced. Okay, so the main meaning is that whenever there is a force, the perpendicular distance between the line of that force, this dotted line is the line of the force, and that pivot, the center through which the axis passes, maybe passing like this, maybe passing like that, I don't know. The pivot is the product of the force and the perpendicular distance from the pivot to the line of action. Their product is nothing but torque. Okay, this is nothing but torque. Understand? Now what are the units of torque, you might ask? As you can see, torque is nothing but force into some distance. So it will be Newton meter in SI. In CGS, it will be nothing but Newton, so it will be dyne centimeter. Now we will now tell about the direction. Earlier, remember I told you that it is a vector quantity. So if it is a vector quantity, it will have direction. Okay, now let's say there is one body like this, a rod like this. If I put a, let's say this is the pivot. Now if I put a force F here, you know the body will move like this. But instead, if I had put a force in this direction, not this direction, if I had put the force in this direction, it would have moved like this. This motion is the clockwise motion, and this motion is the anti-clockwise motion. So whenever in exams, if you write this is the torque, you will write like 50 Nm. You should always write ACW, not I'm writing in shortcut, but you write the whole thing. Okay, clockwise or anti-clockwise, you have to write, otherwise you will not get marks. You need marks. So now I'm going to tell you what is actually positive torque or negative torque. Means anti-clockwise torque is always considered positive torque, and negative torque is nothing but clockwise. Now this is given in the book without any reason, but I'm going to give you the real reason here. Why is it so? Let's take a disc. Let me rewrite this. So it moves to move it clockwise, we have to, no, let's say first we move it anti-clockwise. So we have to apply a force here. Let's say this is the pivot. Okay, so as you can see, the perpendicular distance, this is the perpendicular distance R. So if we draw it separately, as you can see, this is R, this is F, they are perpendicular. Okay, tau is F into R. This is for anti-clockwise. This is a diagram. Many times diagrams also come, but not the reason. Okay, now let's say for a clockwise motion, I put force here, the R is here. So here, as you can see, R is in the opposite side in clockwise. Now if you know a little bit of coordinate systems, you should know this, that if let's say this is plus 5 meter upwards and this is minus 5 meters up downwards, always downwards is like negative, you know this. So as you can see here, R is in the positive direction, and you also should know this, that this side is like plus 5 will be this side, minus 5 should be this side. So this always, let me redraw this side again. If you know the coordinate system, this place x is positive in these whole places, and y is positive in the above places. This is a coordinate system thing you have to know. Now see, if you know here, both Here both F and R are nothing but positive, so tau should be also positive in case of clockwise, no, anti-clockwise. But in the clockwise, as you can see, we know tau is F into R. Now F is here positive, but R is negative, so tau becomes negative. Tau is nothing but negative. This is not given in any book, just telling you should know the reason for everything. If you don't know the reason and just like without anything you just remember everything, like mug it up from the book, in physics not going to help. Conceptual questions will be coming. Maybe they can ask why it is positive, why it is negative. You just write this reason. Understand? Now some common examples. Now no, let's not do this now, because I'll give them all together after doing what we call the couple. This is not a romantic thing, or you can also say that. Let me introduce it to you in a romantic way. So if there is, let's say, a body, and I applied two equal and opposite forces, then these two forces are known as nothing but couple. Anywhere, even that, see, if it was here and here, or even here, or even here, just anything, it has to be equal and it has to be positive. All should be F, and exactly opposite in its direction. Now couple is very useful in daily life. You'd say how? Like, see, if you move a steering wheel, let's say, let me draw this well. This is the steering wheel. So if you always to turn like this side, you apply a force here and you apply a force here with your two hands, and the whole thing turns in this direction. Or let's say if there is a tap, on the tap you can see this is the above of the tap, you always apply a force here with F, here with F, and the whole thing turns in this way. Understand? This is how like everyday things work, and rotational motions everywhere. Understand? Now if I say a moment, a couple action, what is actually the total moment? As you can see, about a rod, okay, about a rod. So about a rod, now let's say at the ends we apply a force here, you apply a force here. Understand? Let's say the pivot is at the middle, okay, so this distance will be L, this distance will be L. Understand? So moment of this, so tau of, let's say this is 1, this is 2, tau of 1 is nothing but FL. This is perpendicular, okay. Tau of 2 is nothing but FL again. So if we add, now if you see, if the force is here, this is anti-clockwise, if the force is here, it is anti-clockwise, so both sides it will be anti-clockwise, okay. Now if it is anti-clockwise in both sides, we'll add the tau, so tau net is nothing but tau 1 plus tau 2. What is that? F into 2L, 2FL, means actually F of D, if we consider the whole length of it to D, okay. D is the whole length. Understand? This is rotation about a couple. Now let me tell you, this D is also called the couple arm. Couple arm, not the arm of the two people. Couple arm. Actually couple arm is nothing but, in simple language, if this is the rod, F is acting here, F is acting here, extend it, the perpendicular distance between the two. Understand? Very simple. Now let's talk about equilibrium. Equilibrium. Can you tell me what equilibrium is? in simple terms, summation of all forces acting on a body should be zero. Meaning, if there is a body like this, many forces are acting like this, so F1 plus F2 till dot 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 Fn is zero. Then I can say this body is in equilibrium. Now, equilibrium is of many types. Now, these equilibrium types are not discussed in details. This is not in the syllabus, but I will still tell it. Equilibrium can be stable equilibrium. Then it will be unstable in equilibrium. And there is the neutral equilibrium. Neutral. These are three main types of equilibrium, same in every life. Stable is like this. Let me give you an example with just a bowl and a ball. Stable is if we put a ball here, okay, at the end of a bowl, if you displace the ball up to here, it will always go back to its main position, because it is, this point is its stable equilibrium point. Okay, stable equilibrium point, that's why it will always go back to its original position. Now let's say, don't put the ball like this, put the ball like this. Now if you displace the ball here, it will not go back here. No, it will always fall down here, so it will never go back to its equilibrium point. Okay, it will never go back to its equilibrium point. So this is unstable. Okay, this is unstable. And neutral is that if there is a ball here, I push it a little bit, it goes here, so it does not go either away or near the equilibrium point. It is in a neutral position. Understand? So main difference is that in stable equilibrium position, if we displace the ball a little bit from the equilibrium point, it comes back to the equilibrium point. If in unstable equilibrium, if we shift the ball away from the equilibrium point, it moves away from the equilibrium point. And in neutral equilibrium, if we move the body away from the equilibrium point, it does not react in any way. It does not go away, it does not come near. Now let's just talk about static equilibrium, because that is in syllabus. Static equilibrium. Static equilibrium. It is of two types: linear and rotational. And what this actually means is that, let's just do the linear first, or the translational. It is nothing but if there is a body like this, many forces are acting on it. As I said, equilibrium nothing means delta F equal to 0. Means all the forces cancel out each other and the body just stays there. That is for the linear only. Okay, just the rotational we are going to focus. Okay, now if there is a rod like this, we apply many forces like this. 1 second, the charge is low, let me charge it. And done. Okay, if there are many forces acting like this and many forces acting like this, so if the net torque is 0 in this case, then we say the body has got rotational equilibrium. It has achieved rotational equilibrium. Now I would say, how, like say, if I say a body here and a body here, so if both are same forces, distance from the center is also same, L, let's say, so it will move in this direction and this will move in this direction. So this one, let's say 1, and this is 2, tau 1 is nothing but FL, and clockwise direction, tau 2 is nothing but FL in the anti-clockwise direction. Understand? So these cancel out each other and the net tau is nothing but 0. Understand? Now we are going to learn an important topic, very important, the principle of moments. Principle of moments. Okay, principle of moments. It states that if a body is in rotational equilibrium, the net anticlockwise moment of force is equal to the net clockwise moment. Understand? This is actually the thing. Okay, now let's say, for you to understand, let's say this is a rod, a body is hanging here giving a force F, and give the F1, this is giving a force F2, and this is the pivot. Let's say the distance here is L1, distance to here is L2. From this it will move in this direction, for this force it will move in this direction. Now the net anti-clockwise moment is nothing but F1 L1, net clockwise moment is F2 L2. This is the actual mathematical form. If you want solve any sum with this, very easy. We're going to do few sums with this. Okay, few sums with this. Let's do the first sum. Okay, first question. Let's say there is a wheel like this, can't draw well, wheel like this. Okay, now here we apply a 2 Newton force, and the radius of this circle is one what is it given, 1 meter. Okay, now it's diametrically opposite position, let's say B A. Now you have to tell the O. So what is the tau at BO and tau at AB? You have to tell me this. Means what is the moment of force about the center O and about the point A. This is what these two mean. Okay, so now let's go back to the diagram. You know, always a tangent is perpendicular to the radius. I'm not going to tell you that. You extend this here, this is also going to be 1 meter. So if you see tau BD, what is the force acting? 2. And what is the distance? Sorry, not BD, I did BD, it should be BO. It is a distance of 1 centimeter, so it will be nothing but 1 second 2 Newton meter clockwise. See, if we apply it here, it is going clockwise. Understand? Now see, here also you can see the distance is just 2 and the force is applying here, so same clockwise. This will be nothing but tau, wrote in a wrong direction, tau AB is nothing but 2 into 2, that is nothing but 4 Newton meter, but in the clockwise direction. Same thing, sorry, use the but. So now let's give you 1 meter scale at the middle. Now at let's give a weight here, weight of let's say 40 GF. Okay, now I put a weight of X. Okay, this is 0, 100, 50, 90, 30. Now tell me, why did I add 500? Mad I am. Okay, now tell me, what is the X so that it becomes in rotational equilibrium? What should be this weight X? We know what. Now let's see this. If this is clockwise moment, this has a anti-clockwise moment. Understand? So you know this. Now we will use the anti-clockwise moment. What is the anti-clockwise moment? It is actually distance is 20, so 20 into 40, 20 into 40. And here what is the clockwise moment? This is a 40 distance, and this X we don't know, equal to X into 40. So this got cut. X equal to 20 GF, or the mass is actually nothing but 20 gram. I think we are going to end it here. If you follow Selena, we have done 1B. We'll start with 1A. Sorry, can't can't do alphabets. 1A will continue with 1B the next day. So thank you and bye.